Hello everyone, this is video number 2 of 3 on curvilinear motion, and in this one we're going to talk about polar coordinates. If we have a particle that's moving along the path here, highlighting in orange, I defined axes such that the distance from the origin to the particle is r, and the angle between the line joining the origin and the particle and the x-axis is theta. Using these, I define two unit vectors. And you'll forgive the lacking of the roof notation for unit vector throughout. If you see e of theta, assume that it's a unit vector. Likewise with e of r. So I define two unit vectors. E of r is a unit vector which points in the direction of r increasing, and e of theta is a unit vector that is perpendicular to e of r in the direction of theta increasing. So we have our two unit vectors. Now, with any type of motion question, we want to be able to have equations that describe the motion of this particle. So if we start with the position, we say that position vector r is equal to r, which is this distance here between the origin and the particle, times sort of in the direction of e of r, as in it's in the direction of r increasing, if we write this as a vector. So we have our position vector, but what about our velocity vector? So we want the velocity vector. Well, that's just the first derivative of the position vector with respect to time, which if we use the chain rule is r dot e of r plus r e of r dot. So how do we deal with this? And to deal with this, we're going to use this diagram that you see down here. The white vectors, e theta and e of r, are the same as the ones in the diagram above. I'm just considering this now moving a time delta t further along its path. And I've exaggerated that the change of the unit vector in the r direction is now highlighted in this yellow line here, which is e prime of r, and the new unit vector in the theta direction is this e prime of theta. If you imagine this is rotated through an angle of delta theta. But we're interested in on these values here, the change in the unit vector in the r direction and in the theta direction. And there's one easy way we can deal with this, and that's to do with arc lengths. If you recall that the arc length is equal to the radius times the angle it subtends, provided this angle is measured in radians. Now, if we take the limit that delta theta tends to 0, this distance between the ends of these two vectors will be exactly the arc length. So we can say that d e of r is equal to the radius, which is this distance from here to here, which is the magnitude of the vector e of r, times by the angle, which is d theta. But in what direction is it? Well, if you notice, this d e of r, is in the same direction as e of theta, i.e. they're parallel vectors. It's in the direction of theta increasing. So this is actually in the direction of e theta vector. What is the magnitude of any unit vector? Well, the magnitude of any unit vector is 1. That's how they're defined. So we can say that dE of r is just equal to d theta e theta vector. If we take the derivative of both sides with respect to time, we end up with e of r dot is equal to theta dot e of theta vector. What is theta dot? Well, theta dot is the rate of change of our angle, or in other words, our angular velocity. Okay, so we have a expression for our rate of change of our unit vector in the radial direction, but what about our other unit vector? Well, we do this in a very, very similar way. We can say that d e of theta is equal to the radius, which is now this distance from here to here, which is the magnitude of e theta, times the angle, which is d theta. And in which direction is this? Well, you should see that this vector is parallel to e of r, but that it points in the opposite direction. And for that, we can write minus er as the direction vector. Again, the magnitude of a unit vector is 1, and I'm going to take the time derivative, so we end up with e of theta dot is equal to minus theta dot e of r. So we've got our two expressions that show our rate of change of our unit vectors. So let's substitute these in and get our values for velocity. So that's now equal to r dot e of r plus r times our value that we showed was for e of r dot, which was theta dot e theta direction. So we can see that we've got two components to this velocity. We've got this component in the e of r direction, i.e. in the increasing radial direction, and we've also got this component in our increasing theta direction. So we can write that v in the r direction is equal to r dot, and v in the theta direction is equal to r theta dot. If we wanted to find the speed, the modulus of this vector, we just do the square root of v of r squared plus v of theta squared. But what about acceleration? Just change colour. I'll go to the left a little. The acceleration vector is the derivative of the velocity of a vector with respect to time, which is going to be the derivative, and I'm going to take this expression for velocity and differentiate this one. So using the chain rule with the first terms, we get r double dot times by e r vector plus r dot e of r vector dot, and we deal with the second term here. We end up with r dot theta dot in the theta direction plus r theta double dot. Now what is theta double dot? Well, that's just the derivative of our angular velocity with respect to time, which is our angular acceleration, and that's in the increasing theta direction. And then we also have the final term, which is r theta dot e theta vector dot. So if I just move this down to here, so we end up with r double dot e of r vector plus r dot. Now what is e of r vector dot? Well, that's theta dot e of theta. Move on to the next term, so we have plus r dot theta dot in the theta direction, sorry, drop the vector sign there, plus r theta double dot e of theta unit vector plus r theta dot. Now times e of theta dot, well, that was minus theta dot e r vector. So now we're going to collect terms, and so we can say that a vector is equal to, so in our r direction we have this term, and we also have this term. So that's equal to r double dot minus r theta dot squared, and that's in the e r direction. And what about our component in the other direction? Well, we have this term, and this term in the theta direction. So that's going to be r dot theta dot plus r dot theta dot, which is 2 r dot theta dot, plus this term, which is r theta double dot in the e theta direction. So now we can clearly say that the acceleration in the radial direction is equal to r double dot minus r theta dot squared, and that the acceleration in the theta direction is equal to 2r dot theta dot plus r theta double dot. And again, if we wanted the magnitude of the acceleration, which is this term, that would be the square root of a of r squared plus a of theta squared. Okay, thank you for watching the video. Part 3 will be on intrinsic coordinates. I'll see you next time.